Rebecca. This is take 3 of my homework 1, problem 58 pencast. So we have two 5.0 grams of point charges on a 1.0 meter long thread, and they repel each other after being charged to positive 100 nanocoulombs. What is the angle theta? You can assume theta is a small angle. So from there, that's kind of a big tip. We're going to use the small angle approximation. So if this was like on an exam, make sure you have that in there because it's kind of like a free point that's kind of given to us that kind of like tells us like what's going on. So we're, if we have theta, we can obviously assume we're working with triangles, and that's kind of what we're given here with the line of symmetry. So I drew another triangle here because my diagram was not that great. So we have a right triangle, and then this is our theta, and then this is would be our d divided by 2 because our d is like in half, and like d total is like the total length, but we're only looking at half of it for the first part. And so we have our knowns and our unknowns. We have Q is a positive 100 nanocoulombs. Our mass is 5 grams. Our length is 1 meter, and our two unknowns. I don't know if I said this already. Okay, so that's our step 1, is just identify our knowns and unknowns. And our second step is draw your y and x coordinate, and then from there you orient yourself onto the diagram that's given, and then you would draw your free body diagram. So our first one would be the tension on the string with the point charge, so it would be tension. Our next one is the force of gravity, which is the mass times the gravity of the point charge. So that's this vector here, or this, yeah, I think that's a vector. Yeah, it's a vector. And then this is the force of 2, because that's Q2 on Q1. So that's force of 2 on 1, and that's kind of like the repelling force, so that they're not together because like charges repel. And then this is our F net equation. So that's the tension plus the force of gravity plus the force of 2 on 1, which is equal to 0, and that would be like our total, and we're going to use that to find our theta. So our force net, I actually wrote out that it's T sine theta, but that's actually incorrect. We'll talk about that later. I kind of got ahead of myself when I was like going over this. So it's just going to be T of x, and then we'll define T of x later. And then we have our force, does that look good, plus force of 2 on 1, and that's equal to 0. And then this is for the x direction. And then we have our force net of y, which is equal to our tension of y. Actually, wait, yeah, we have a tension of y, so it kind of goes off in the y direction. So we can assume that this is going to be for our force net y equation. And then we have we actually don't have a force of gravity vector in our x equation, and that's because here x is 0, so we don't really have to worry about it. So we would just look at these two equations, force of net x, and then force of net in the y direction. We're going to use the tension of y because it goes off in the y direction, and then we're going to use, actually we would not use this one because if you can see, it would be like 0, and then as far as this vector goes off, so then it would be force of gravity in the y direction. You kind of don't really need to specify that it's in the y, but I'm just going to do that, and that's equal to 0. Okay, so then now we can use these equations to orient it on the triangle diagram, and then that way we can actually like give into perspective what the tension and the triangles, I keep saying triangles, we can use, I guess, a more defined way of what t is, because t isn't a number that's given, so we can use the lengths of the hypotenuse and the adjacent and the opposite sides to identify what t is. So we have our x, which is t sine of theta, and then that's for this. Okay, and the reason that it's t sine of theta for the x direction is because we have opposite over hypotenuse, so that's like SOHCAHTOA, so that's t sine of theta minus f2 on 1, which is equal to 0. And the reason that it's this is because if you look at our force diagram, so tension is going in the positive direction and this is going in the negative direction, so that's why we subtract this. And then our y is t cos of theta, and that's because we're going to use this side for our y direction, and that would be because, Okay, where's our y diagram? So we have y, and we're going to subtract this. Okay, so this is positive still with the tension, so that's why it's positive on this side, and we're subtracting force of gravity because it's going in the negative direction. So that's force of gravity, which is equal to 0. Okay, so then we're going to look at our t sine of theta. You can start off with the t cos of theta, but you know, like it's on top, so you're probably just going to start with the top one. So you can do t sine of theta, and then we're going to move our f2 on 1 to the opposite side. So it's going to be positive now. And then our f2 on 1, can you tell if this is a subscript? This is a subscript. T sine of theta. Okay, so f2 on 1 is actually the 2-point charge equation, and that's going to be k, and then this would be q1 times q2 divided by d squared. And then d is like this total r. It's actually d divided by 2, but we'll just go through that in a bit. So then we're going to go to solving for sine of theta. So sine of theta is going to equal d divided by 2 divided by L, and then that's going to give us d, which is equal to 2L sine theta. So then from there, from there, so now that we have it in terms of L and sine, because L is given, sine is, well, it's not given, but we know more about the sine that we would from D, so we're going to put everything into like terms, and that's just going to make it a lot simpler, and we can use this equation to go back into this equation. So that's going to be, can you guys see at this point? Is it too far? Okay, good. I'm using my coffee table, so it's a little bit hard to see on like my side. So TL sine theta is equal to Q, and then I'm just going to make these two just Q squared because they're the same charge. If you remember that it's Q is equal to the positive 100 nanocoulombs times, what is D? D is 2L sine theta, and then we're going to square it. Oh, and D divided by 2 is because D is half of this length. If you remember, I said that earlier, and that would be this length as well. So then from there, we can, I guess, orient this equation into t cos theta. So for t cos theta, we're going to also move our F force of G to this side, and force of G is just mass times gravity, so that one's a little bit easier. Mass times gravity. So we're going to do t cos theta equals divided by mass times gravity. And then these two go out, and then we get tangent of theta. Can you guys see this? Okay. This is going to be kq squared for L squared sine squared theta. And then from there, we're going to kind of want to move all our sines and our tangents to one side. So that's going to be sine squared theta times tan theta, which is equal to kq squared divided by 4 squared. And then times mg here, but it is divided by the top. And then from there, this is just kind of plucking the numbers from the, at the beginning. And I'm actually going to move them to this side so we have a little bit more room, if that's okay. So we're going to have sine squared theta tan theta, which is equal to k. And k is, if you look at your equations sheet, it would be 9.00 times 10 to the 9th newtons meters squared divided by coulombs squared. I wonder if I'm going to have enough room. Okay, my eraser is moving. It's power. Ignore that, that was weird. So then we have, okay, so our q squared is 100 nanocoulombs. So if we have nanocoulombs, we know we're going to have to convert to regular coulombs in a bit. And this is squared. Then I'm just going to do this. So we know that this is the top half. And then we're going to divide by 4 times our length, which is 1.0 meter, 1 meter squared. And then we have mass, so our mass is 5 grams. And then again, we have to convert grams to kilograms because that's not the proper SI unit. And then I think that's it. Gravity. 9.81 meters over second squared. Okay, and then from there, you want to multiply by our nanocoulomb configuration. So 1 coulomb is equal to 10 to the 9th nanocoulombs, also multiplied by 1 kilogram, which is 1,000 grams. You could also do this like in your head, so it would be like 1.0 times 10 to the 7th, or to the negative 7, but that's also like an easy way to lose points on a test, which is like familiar to everyone, so it's just an easier way to do it. So this would give us sine squared theta tan theta, not squared, and then we get 4.59 times 10 to the 4th. Okay, and then this is when we can use a small angle approximation, and that states that the angle between the angle is like really small, so basically sine theta is equal to tan theta or cos theta, but right now we only have tan theta and sine theta, so that's what we're going to use. Approximation, and that states that sine theta is equal to tan theta. So we can get everything in terms of sine theta. So we have sine squared theta times sine theta. This is our new sine, which is equal to 4.59 times 10 to the 4th. So it's equal to sine to the 3rd theta, which is equal to 4.59 times 10 to the 4th. Oh wait, this is negative 4, isn't it? Yeah. Sines are important. And then you take the cubed root of that. And that's going to give us, actually, you take, yeah, that's fine, is equal to 0.07714. And then from there, you take the inverse sine, which is going to give us, you could have also done this in like a different way with your calculator, but I feel like that's an easy way to like skip points as well. And it's going to give us 4.4 degrees as our total, and then you can like check on that because it did say we were going to use a small angle approximation, and 4.4 is a small angle. Yeah, so thanks for tuning into my pencast, and my name is Rebecca Ramirez. I don't know if you saw that in the little corner.